Okay, so the first one someone asked was these last two slides, and so they asked about this particular question, and this question is just asking us how we can convert this acid into this acid. So all we're doing in this problem is adding a CH2 group from this one on the left to this one on the right. We're extending the carbon chain. So how would we do that? We've learned all of these reactions in this course. So what we're really going to do is we're going to get to the point where we can add something to this to make it one carbon longer. And that's not that difficult. All we have to do, the first thing we want to do, use this strong reducing agent, and this will reduce our carboxylic acid to an alcohol. So once we've done that, now we need to extend the chain. We need to somehow form a carbon-carbon bond. We don't really have any good ways of making a carbon-carbon bond with this, although we could. We could make that a better leaving group and then react it with sodium cyanide. But I'm going to use PCl3, and when I do that, make this chloride. Can you see that down here? Okay. Then I'm going to react that with sodium cyanide. Okay. So we covered this in chapter 11. It was in there. This just converts the alcohol to an alkyl bromide. And if you take a look at one of the videos I put online yesterday, and for those of you who were here yesterday, we talked about the fact that we can go from alcohols to alkenes to alkyl bromides to epoxides. All of those things can go back and forth. So that's what you want to be thinking of for synthesis. So this one now, we're going to form a carbon-carbon bond. Don't forget, whenever you see sodium or potassium, it's a cation, so its partner has to be an anion. This particular anion, the cyanide anion, we'll just do an SN2 reaction and get rid of the chlorine and form a carbon-carbon bond. So we then make this thing. Which is a nitrile, okay? And our nitrile can easily, well, not easily, we have to treat it kind of extremely, but we can treat it with water, and we can do this with either acid or base. Both will work. We also have to add some heat. That's what the little triangle means. This is a stubborn reaction. It will make the amide but as long as we keep up this heat and water under acidic or basic conditions, it'll get all the way to the carboxylic acid. Okay, so we've just extended our carboxylic acid by one. Notice that this carbon came from this cyanide, right? We made that carbon-carbon bond. We lost the chlorine and we made an extra carbon right there, and then we hydrolyze this. It goes to the amide and it keeps going. Amides will hydrolyze under forcing conditions. Remember, we had to heat them because they're not very good electrophiles, but we can, and we can get them all the way to the carboxylic acid. Okay. Now the other question, which was on the slides that this person asked us to take a look at as well, is we're going to react a nitrile, and from it we're going to make a ketone. So how does that occur? And we're actually going to cover a couple of reactions here. By the way, these are from slides 84 and 86 in the carboxylic acid derivative chapter. So now we want to react, I'm going to react a nitrile with, I'm going to react it with this. Grignard reagent. So we could make that Grignard reagent. All we have to do is get a alkyl bromide or an alkyl chloride, and in this case we used an alkyl bromide, reacted with magnesium. We get the Grignard reagent. Remember, this is a very polar bond. We want to think about this as being ionic. We want to think about it as being like this. That's a 2. It's a very good nucleophile, very strong nucleophile. And that's just going, now when we take a look at this, we take a look at the periodic table, nitrogen's more electronegative than carbon. So this is a polar bond. It's going to be slightly positively charged there, slightly negatively charged there. The nitrogen's a little bit more electrophilic, so we're just going to attack it in a nucleophilic attack of the nitrile carbon. Okay, the electrons that are here are both going, and then we're going to pop a pair of electrons up into a lone pair on the nitrogen, and this will form this thing. Let me put both pairs of electrons there. Okay, so that should look a little bit familiar. That looks like an imine, and we can think about, okay, if we just somehow protonate this, react it with water, whatever, but let's throw a bunch of acid and water in, a bunch of acid and water. The first thing that's going to happen, that acid's going to protonate that negatively charged nitrogen, right? This is kind of nice because now we're going to talk about this is an imine. And remember, we made imines by reacting amides with ketones to make imines. This is the simplest of imines because we don't have an R group on the nitrogen, we just have another proton on it. But it should hydrolyze just as easily as imines do. And we have a bunch of acid and a bunch of water, okay? And what do we do when we see a proton? Remember, I've talked about this a couple times the last week or so. I've been talking about it all along, but I'm really emphasizing now. We see these great big mechanisms. Students get a little worried, do I have to memorize that mechanism? And the real answer is, you could memorize that whole mechanism, or you could do it step by step, because a mechanism is just all of the elementary steps to get us from reactants to products. Okay, each one of these steps we're saying is an elementary reaction, and it makes up this complex reaction. So now, what do we do? Our next elementary step, we threw lots of acid in there. We're just going to protonize this. Just a proton transfer reaction. When we make that, we have this thing. Actually, I'm just gonna now get lazy and not put my CH2 in every time because I'm not gonna be doing anything there. All my chemistry is gonna happen here now. So I protonated it. I could draw a resonance structure that would put that positive charge on the carbon and the nitrogen being neutral. We would just kind of throw those electrons up there onto the nitrogen as a lone pair. Then we would have a carbocation. And we have lots of water around. So this thing is a pretty good electrophile. It's positively charged. We have water, not a particularly good nucleophile, but we have a very good electrophile. We're just going to form an oxygen-carbon bond. We're going to throw these electrons up there on the nitrogen. There's my CH2 and my CH3 group. I'm going to erase this stuff now because this tiny board, because I want to keep going. We finished that, so we're good here. We don't need this anymore. We're kind of in a way, we added the Grignard reagent, and then we protonated, we got the imine. We're now doing the hydrolysis of an imine. We protonated that imine to get our iminium cation. We've now reacted it with water. What's the next thing that you want to think about doing? So I'm going to cheat. I'm going to go through. Something's going to come along and take that proton off. Then I'm going to have the neutral compound here with something that's dragging a proton around. Then the protein's going to float around and it's going to come up here and put a proton there. Okay? So I pull a proton off, get my neutral compound, and then proton comes along. We're just doing a proton shift. We're doing a series of proton transfer reactions. One's pulling off, then it's floating around, putting it on somewhere else. All of these reactions are reversible after we've added the water. So now we have this thing. Okay, and that can leave, just like water could leave, this is going to leave as ammonia, okay? I'm going to push it off. I don't have to. I could just do this and have a kind of a carbocation, but I'm going to push it off, and I'll tell you why I'm going to push it off in just a second. So I'm reorganizing these electrons to make a carbon-oxygen double bond and kick off that thing as ammonia. There we go. And NH3. NH3 happens to be a pretty good base. It's going to float around. It's just going to rob this proton off of here. And we're going to end up with our product that we want. I'm going to draw it a different way. I'm going to draw it like this. And I'm going to erase this up here just so we can put this in a box. And our NH4. That's going to be happy. And there's our ketone product, okay? So this is actually something you haven't seen before, but I would expect that many of you, and some of you may not get there, but most of you are going to be able to figure this out, because the first step of this reaction, we made a strong nucleophile, and we just reacted it with the only electrophilic carbon we saw in that starting nitrile. And then from there, we easily see, oh, we can protonate that, we get an imine. Then we need to recognize, oh, imines are not very stable under acidic aqueous conditions, so we just throw a whole bunch of acid and water at it, and you're able to make and isolate this ketone. And these go in very high yields, okay? How many people think they would have been able to get that before today?